This video is covering an example problem where we're doing a combination of downsampling followed by digital demodulation. Okay, so the setup for the problem is that we have a message signal, okay, so M of t, that has a certain Fourier transform M of f. Okay, so here's the transform, and we see that we're assuming a certain bandwidth of the signal, baseband signal with a 15 kilohertz bandwidth. All right, so the next step is that we're going to take M of t, we're going to modulate it. All right, so I give you a modulator frequency. Turns out it's 101.3 megahertz to have a signal I'm calling R of t. So visualize transmitting the signal. All right, and at the receiver end, we know we'd take the signal, assume the channel is perfect. At the receiver end, we get R of t, and we sample it. Okay, in this particular case, I'm going to use a sampling rate of 96 kilosamples per second. And so the question becomes, all right, from there, we're going to do digital demodulation. Okay, so what is the frequency f naught? All right, so find f naught. So which frequency should we use for digital demodulation? And will it actually work? All right, so it turns out there are certain combinations of FC, FS, and F naught that will work. And so the question is this one of those? All right, so we're also trying to answer that question. Okay, so in this work, it turns out that when you sample, what we know is sampling replicates the spectrum. All right, so our process would then be take the replicas. All right, so we start at FC and we subtract off multiples of FS. So FC minus some integer value n times FS should eventually land in the Nyquist interval. So here's the Nyquist interval. All right. Well, to find that, it can be kind of tedious. Here's a way that you could work that. You could find the exact value, not worry about them being integers, find the exact value for hitting the lower end of the Nyquist interval, the exact value for it hitting the highest end of the Nyquist interval, and then choosing the integer value that shows up in between those two exact values. All right, so that's what I did here. So in this particular case, FC was 101.3 times 10 to the 6th. FS we took to be 96 kilohertz, so 96 times 10 to the 3rd. All right, plug that into this first formula. You get the lower exact value for n, which is 1054.7. Plug into the second equation, get the upper value, which is 1055.7, and so the integer value between those is n equal 1055. All right, so you plug that value of n back into here, and using the values for FC and FS, you get 20 kilohertz. All right, so the question is, does this work? And the way you can tell is you sketch the spectrum. All right, so I know that the spectrum is now centered at 20 kilohertz. Okay, so that was a little bit wrong. This is 20 kilohertz. All right, and I know that the bandwidth of the signal is 15 kilohertz times 2, so 15 in each direction. So this is 30 kilohertz. All right, so this upper edge would be 35 kilohertz. And then I look at the Nyquist interval. This is what matters. Does it fit within the Nyquist interval? And yes, 35 is smaller than 48. So everything worked. All right. And so this technique of downsampling to a lower range is useful for digital systems because it's hard to make a really high-speed sampler. All right, this lets us get away with a lower speed, lower sampling rate, and yet we can still do the demodulation step digitally. Okay, so you might have the question, well, show me something that won't work. All right, so this is a fact you should know. You should know that some values of FC, FS, and F naught do not work. They don't just fit correctly within the Nyquist interval. All right, so for example, if we change the sampling rate to 48 kilosamples per second, okay, going through this inexact, N E1, N E2, okay, sounds funny to say inexact because what I mean is NE, the fractional value of N instead of the integer value of N. Okay, so if you go through that same process that we did for the 98 kilosamples per second rate, then it turns out the N value is 2,110. All right, so we plug that in, and again we get 20 kilohertz. All right, so if I sketch the spectrum here, I know it's centered at 20 kilohertz. All right, but then my Nyquist interval is minus 24K to plus 24K. All right, and the bandwidth of the signal extends further out past the Nyquist interval, so this part would actually wrap back around, which would give you a distorted signal. All right, so with this particular combination of FC, FS, and F naught, this digital demodulator will not work. All right, so hopefully this is an illustrative problem. This is a common approach that's used when people do digital communications.